All right, let's start the second panel. Hello again, everyone. I hope you have enjoyed so far the talks. You had great talks. We had a great panel in the morning, and then this is the second panel. We have great panelists regarding sensing and sensing algorithms panel. So you have Dr. Julian Yordakita from Johns Hopkins University. I don't see Emad yet, but I had seen Dr. Bakhter from Johns Hopkins University. Emad, if you're there, please turn on your camera. And we have, I don't know, Sam, your first name, I can't pronounce it. Can you?
Just
okay.
Dr. Just Ao. Just
Ao. So, okay. Sam Ao from Chinese University of Hong Kong. Yeah, awesome. Nice. And we have Dr. Christos Bergels from King's College London and United Kingdom. So thanks again for participating in today's panel and for your time. So I'm going to stop sharing to then being able to just talk. So we have another actually moderator, Farouk. He's going to join soon, but before he came in, I want to start with the first question. Feel free, any one of you, come up and answer the question. The very first question is that, what do you think about the title of the basically workshop? Basically, holistic design and sensing and control once we are dealing with or fabricating, you want to design and fabricate a medical or surgical robot. How do you consider do you consider this at all once you want to make a new robot or start designing a sensor or not? So we saw actually in your videos basically different robots or 4 different robots. So then my question is that, is it important holistic integration of design, sensing, and control, or which one is important? How do you look at it? Anyone wants to go first? Christos, do you have any idea? I mean, what do you think?
Yeah, I'm trying to find the raise hand button, changing place depending on the Zoom.
Yeah, go ahead. Don't need to actually raise hand. So it's yeah, go ahead.
Yeah, I think it's a very important topic, and there has been a variety of research that investigates, the design of the robots, but also where you should place the sensor of the robots. Like some work from Mark Mahoney comes in place. How should you sensorize systems to get the best information, especially for continuum robots? But ultimately, they are all also coupled. So it doesn't mean that you need potential to do everything, but understanding the shortcoming of your own system. Let's say you're not able to integrate sensors. Can you embed in the design some characteristics that will allow you to cause harm up to a certain extent? Or and then maybe one of those lacking could be mitigated by some extra thought in the other components. Or conversely, you could add intelligence through visual means, and then perhaps not have to accommodate too many sensors. So it depends on your space constraints as well. So I think definitely the workshop is very timely. I think the new systems we start seeing, they do have these 3 components. So yeah, I'm looking forward to hearing the discussions.
Sure, Sam, what do you think?
Can you hear me properly?
Yes. Yep.
Okay. Perfect. So I mean, when we say robot, I guess you are mostly talking about because when I look at robot, we talk about back end and front end. The front end is something like an instrument touching on the patient. For those items, I think pretty much, I think looking at the problem from a holistic design is very important, because the size become very important. And also like pretty much we are talking about couple millimeter diameter instrument. So if you don't think about everything together, pretty much you cannot accomplish the goal. The other thing is about for something touching on the body, is very different from the part of the arm. The arm itself doesn't need to touch on body. They can be draped, or they are very remote from the body. So they don't have any sterilization requirement. They don't have any cleaning requirement. And because they are bulky, so you can put a bigger motor, you can put a bigger sensor. So everything is easier when you are talking about the back end of the system. That's why when we are talking about buying a robot arm from KUKA or UR, things are easy, because you are talking about bulky stuff. But anything putting inside the body, I'm pretty sure holistic design is important, because for example, when you are picking sensor, you cannot put an encoder inside instrument. Even though you put some other sensor, it may not be sterilizable. Then you make your instrument to be single use. So it will change it will shift the whole paradigm of the design. And also the control will be totally different. So that's why when we talk about a holistic design, maybe the first question we need to ask is which component you are talking about in the medical robotic design. So I was mostly looking at that from the instrument design perspective. We need to have a holistic design, but from the back end, the arm design, maybe you have more freedom to doesn't need to combine them together.
Perfect. Julian, what do you think?
Yeah. So definitely, thank you very much again for inviting me to this interesting discussion. And I think in our experience that also in collaboration with Farshid, we learned this problem on the hard way. So basically, when we start actually designing, building our continuum manipulator, and our problem, it was okay. Now we may be able to control, maybe based on the model, but if the model is not, precise enough, how could we bring the, shape sensing into the image here? And at one moment, we learned that our design wasn't good enough for embedding the sensors, at least what we were planning to do. And we went back to our design, improved the design, and after that, tried to test it. Now, we learned also that even if we have the sensor in the right place, it may not work. And in that case, we are trying to see how to help with our sensing capabilities. So I think it was a good lesson for us, and definitely when we will try to design new such a kind of sensing capabilities in another snake, we need to have such an approach, holistic, to understand better the application, how we build the robot, how we control, what kind of feedback we have to send, what kind of errors we may generate, and how to mitigate all these problems. Sometimes maybe just one sensing technology may not be enough for what we are looking for, and we may need to bring other, sensing capabilities. So I think, we are trying to learn how to have such a kind of approach. What is the best solution? But I think holistic is a good term to describe all these matters.
Great, thanks. Ahmad, go ahead, please.
Do you hear me?
Yes.
All right.
Go ahead.
I'd like to thank you, thanks Farshid and the organizer for creating this opportunity and for inviting everybody to discuss. So I mean, if you think about it again, what's the alternative? If we're not going to do it holistic, so what's the non-holistic approach? We'll be buying a robot off the shelf, buying a sensor off the shelf, try to put them together, and at the end, we expect that maybe, depending on the application, if we're operating on a diagnostic application, so the medical robot is supposed to do really non-invasive or diagnostic task outside the body, then yes, we may be able to perform just well. But now, as you're getting into a very compact Dexterous device, and we cannot do that. So for sure, holistic design for design and sensing, it's a necessity. There is no way out. And in my opinion, it has to be driven by the clinical application. What is it really needed? So it's like apply the lean approach exactly. And when we look for like how to do translation research, and we're not asking the engineers, we're asking the end customers. So we will have to do this, and we're not just asking the clinician. We really want to go back with the requirement, go back to the team, and have the robotist and the sensor scientist, optical, ultrasound scientist, and the computer science all in the same room, iterating the prototype once and twice and 3 times, because it's better to have this iteration in the design and prototype phase before you go into serious translational phase. And maybe I can give a couple of examples. Like for example, if we really want to, and I will highlight that in my talk at the end of the day. If, for example, we want to have a small dexterous robot, and we need an ultrasound imaging device, right? then we have two options. We can just go and ask one of the ultrasound company like Vermont, please, we want to design for us a tiny little microarray that will be a 3 millimeter in diameter, 10 millimeter the aperture length, and pretty much package it, make it as like end product, and we will try to put it into one of these snake robot or continuum robot. It can work, but let's just ask this question. It will be a separate system. It will be quite expensive. It will take quite big space and size from this tiny robot that you're trying to do. And the questions we have, can we do it better? Do we really need the ultrasound sensing, for example, for the whole duration of surgery? If we just need the ultrasound to help us only in 10 minutes during 2-hour surgery, then it doesn't make sense to occupy 1/3 of the space of a tool like that. And then is there a holistic idea that we can simplify the ultrasound and leveraging the ultrasound via robot tool? And these ideas do exist, because if we can have the ultrasound very small, very cheap, only single element, single point, and we take advantage of the fact that the robot can move precisely from point to point, then the robot can help do the imaging. And now we have deep integration, and that's probably what you mean by holistic design and sensing. So that's pretty much my view, and examples are endless, really.
Thanks so much for the actual example. Go ahead, Julian. You have something to say.
I would like to add another example here, continuous Imad's idea. So in our application that was done with Farshid and Sharia from Hopkins in collaboration with Professor Armand, our problem was to design a snake that will go behind of acetabular cap and try to remove the tissue. So basically the snake has to interact with tissue, also with obstacles in the workspace. So one problem was, okay, if the snake will be in contact with an obstacle, and we still could control, the snake by actuating the wires. But in order to predict the position of the snake, we have to know if one part of the snake will be stopped, and we could still, actuate the other part. We have to know, what is the leg of the snake that cannot move, such that the Jacobian of the robot will be updated in real time and still try to control the robot. And I think here Farshid and Sharia, they did a great job. But the problem was how we detect the contact point. And where is that contact point? So for this reason, we are trying to use optical fibers, and we kind of achieve half of the goal. We know that we are touching, that obstacle, but not exactly where is a contact point, and that was because of limitation of our sensing technologies that we are using. And but this could be solved in the future, and there are other people trying to solve this, because such a kind of approach will help, to understand what kind of sensing capabilities we need to provide. So I think this is a very good example where this holistic approach will a little bit help us, to decide on the right technology for the shape sensing of continuum manipulators.
Awesome, thanks. Sam, in your design of the new robot, I think it's the same problem. You have a sort of like device that can bend in the sort of not a straight trajectory. How did you consider, if you want to sense the shape, what type of sensors you have in your mind, like optical fibers, external imaging modalities? How did you tackle this problem in your basically new design?
So my new design is related to articulate joint. So the bend radius that we are having is quite pretty sharp. So if you want to, we are not sending the shape direction. We mostly need to sense the angle at the distal end. So definitely you can use optical like a fiber which is something we are planning to do, to put it at the center of the instrument. Because if you put it on the side, there's a chance the band radius at some location is tighter than the minimum band radius of the fiber, which may not be feasible. But if you put it in a standard continuum robot, that may work. So, and then in the meantime, we are also working with Intuitive Surgical, and then we have their own like a lunar sensor to do some research on this area. So pretty much I will go for optical fiber to measure the shape and angle at the distal end. That is the classic approach that I will be using. Yeah. And given the size, I think at the end, I think summarize what other panel members have discussed is, I think the fundamental problem is the dimension is pretty small. We are talking about a couple millimeter diameter, which is hard to put other sensor to be precise and give us enough information. That's the reason why we are targeting for holistic design, in particular for the sensing, we are looking for optical fiber. And also we need to deal with sterilization and cleaning and reliability issues. So I think, according to my experience, sounds like at this moment, optical fiber approach will be one of the good solution for this area, unless some people have some other like a very small encoder or some sort of like a force gauge or something like that. I don't know, but I haven't seen anything that will be able to use for medical world easily at this moment. But so far we can see optical approach is the best one.
Okay, Christos, what do you think for your concentric tube robots and your delicate actually environment that they are working? What was your approach? How you're going to sense your robot?
I mean, so we haven't managed to sense shape right now. I mean, in the location where we are now looking at, you can see the shape. So we would be interested more in contact force sensing at the tip, which you could do with optical fibers, not necessarily fiber Bragg gratings, but you could use, intensity reflection techniques as well. I mean, I know, Julian has a lot of experience on the fiber Bragg gratings, and it seems that many groups have managed it. It's a big capital investment as well to work with these sort of systems. Like you gotta be pretty certain that you will nail it, because otherwise you are, like 60K short or something. So anyway,
it's very true.
Yeah. So we tried to do exteroceptive force sensing, so to create some sort of miniature tactile elements that cover the surface of the robot, and we looked into piezo resistive materials and made circuits, and then we were able to let's say surround a cylindrical tool with it, and still you could flex. They didn't work that well, but I mean, if in terms of research, I would say that sounds very exciting to me. Like looking into micro manufacturing, what sort of small sensors can you make? Can you read out? Because then you could have true direct sense of how the instrument is interacting with tissue. And of course, for shape, though, I think that the optical fibers is probably the way to go, especially if you can't see the robot.
Well, I would like to say here something like optical fibers. It's not a general solution for all this application, of course, and it's not only a matter of price. I totally agree that a starting price is a little bit high, but the technology is going down, and I guess it's our by doing this research and showing to the community that shape sensing using optical fibers, it's a good solution, and that will create a need on the market, and that may go down. But I don't think we should necessarily consider the optical fibers as the first option. It depends on a lot of factors, size. If it's a continuum robot with, local deformation or not, if it's a real joint, you have a lot of local deformations, optical fibers are not good. Also, you need to consider sterilization. So, and we know very well that, these optical fibers, you need to attach, to fix, to glue them on the elastic element. And, based on what Professor Patel group show us, it maybe that glue will take maybe 6 or 7 cycles. So there are a lot of other issues that we need to consider once we decide the optical fibers. Now, of course, we could go with other type of sensor like regular strain gauge that will still give us similar information. If we have a bigger snake, that it's a good solution. So the problems are a little bit more complex, of course, and I will say we could try to identify what does mean an ideal, sensing technology that will fit everything. And I don't think we could are able now to say this or that technology is the best one. So it depends on the application, of course.
Totally agree with you. Wanted to ask this from Emma. We're just talking about embedded sensors, right? How about external imaging modalities, right? So you are an expert in photoacoustic and ultrasound. What do you think? I guess we are just sticking with this, but we have other external resources that we can actually use.
Sure. Maybe I can share my experience working with ultrasound and try to add it to robotics elements. So we have, for example, we want a robot to automate and provide kind of power steering ultrasound imaging for sonographer. So it wasn't a problem at all, as I said before, to have a probe like this off the shelf, a wireless ultrasound probe. You hook it onto UR5 or KUKA, and it does the job. But when I tried to adapt the same approach, and I have a conference paper published with Nabil several years ago, where we try to get getting a complete microarray from Vermont and Siemens. They provide this array, and we basically try to put it into one of Nabil's robot. It was a very good first step, but we learned from this that we probably need to modify and adapt. And basically, there's 2 elements. It's either we need to design the robot from the beginning with the ultrasound, or we design the ultrasound to make it as small as a single point, right? And there are restrictions on both. So my approach is going into 2 different directions. So it really depends on the clinical requirement. If there is a need for ultrasound imaging or functional imaging, right? Because the robot is doing a critical operation and may cut a nerve here and there. And then we need for this Dexterous robot to be able not just to do the action, but to sense the presence of critical structure and give early warning to the doctor to avoid cutting it, right? So this sensor becomes quite complicated. You want it for anatomy, you want it for nerve, you want it for a positive margin of cancer. How are we going to do that? Shall we put a system for every task and try to kind of like find a way to put it all in one small system? It's really impossible task. So one approach to solve this problem is to go to an ultrasound array designer and tell him, let's just use the material of the robot itself as the PZT element. So build up your robot from a PZT alloy. And now the structure of the robot is going to be the array itself. And that will be the kind of like extreme deep integration or holistic design between the sensor and the robot. But at the same time, there is another approach, which is, I have to admit, I focused almost 10 years working on this approach, is the photoacoustics. Because photoacoustics effect or phenomenon is quite attractive. We don't really need sophisticated ultrasound system like this one, where we have an array with backing material and separate channels to transmit and receive, and everything has to be in the same device. We can separate light from ultrasound. And that was very, very attractive feature. So now we can have on the tiny robot tool, even if it's a sub-millimeter tool, we can have a tiny 50 micron fiber. This fiber delivers light, and the light generates photoacoustic effect. And now we can have the imager somewhere else, away from the robot scene. And this is where, I'm actually going to describe it in a bit detail in my talk later this afternoon, is I thought to myself that if I want to have holistic and deep integration with these tiny tools and tiny robot Dexterous robot, the requirement for me is to have my imaging system to be single point. That's the smallest I can do, right? And we cannot do it, unfortunately, with ultrasound array because we need an aperture to maintain certain resolution. But what we can do is through photoacoustic effect. I can just send the light from the single point and have the imager separated from the surgical scene or from the robot, where the imager can be stationary, it can be as big as this array, and build us an anatomy image in real time, build us now a functional imaging of the cancer, nerve mapping, all of the above. So in my opinion, photoacoustic sensing, I see big role and big future for Dexterous robot and miniaturized tools.
Amazing, actually, perspective. First of all, again, sorry, we should have put your video actually before this session, but our audience should know that we have this amazing talk from Emad. It's like before the general session at 4 p.m. Make sure that you watch it. And we have another clinical talk from a surgeon. That's amazing. Make sure that you watch that one too. So I want to ask the follow-up questions. We are just talking about the hardware, right? How about the model? How about the algorithm? That, let's say you have a sensor like FPG or like basically other imaging modalities. Obviously, they are not perfect. So the data that they are returning, we need to polish them, right? So specifically for FPGs, we know that depending on the calibration that we do, they are not perfect. So how about the importance of modeling? How do you think that we can improve upon those, and what are the approaches that we can do? Should we go with an analytical approach, data-driven approach, or anything? So what's the best way to help hardware that gives us like reasonable data rather than some like noisy data?
Well, I could start on this because you just mentioned FPGs. And by the way, it's not only FPGs, fiber Bragg rating, so there are also other type of FPGs, and it's not necessary, you know, what we like to have a distributed shape sensing, so that it's definitely much better. Also, I would like to mention just to related to what Imad mentioned. Well, because we have snake-like robots, continuum manipulator, so if we are looking just to track the snake tip, that is a problem. If we are looking also to see what happened along the snake, that is a different problem. And this is where we need, you know, to very clear identify a possible solution, because in our application, we are trying that initially is done under fluoroscopy. We are trying to come up with a solution using fluoroscopy to identify the snake shape. And it was kind of working, not real time, but still okay. But there are errors. Now, talking about errors, let's go back to Farshid's question. So, if we are using, for example, optical fibers, these are optical strain gauge. So they need to be attached on an elastic element, and they will give us information about the deformation of that element. Also here a parenthesis, our snake has large curvature. So basically, if you take the glass or whatever and you bend at how much is supposed to be bent, you'll break it. But the problem is how you connect the sensing element on your snake to determine the shape of that elastic structure. So basically, first, I have the fiber, I attach that to an elastic element that will deform along with the fiber, and I need to determine the curvature of that element, take that element and put inside of the snake. Now, that element could be the snake itself, but the problem is I am able to measure some strain in my optical fiber, and how I could connect that with the snake curvature. So what we did, in the first step, we calibrate the sensing element, put inside of the snake, and calibrate the whole system, you know, snake plus sensing elements. And that was based on, you know, taking the measurement calibration. But it's time consuming, and there are errors. This is why actually Sharia, our Sharia Sefati, he come up with a different idea. Let's try to, use machine learning. So it's data driven. So we don't care about the sensor it will be, just put the sensor there, deform the sensor, use a tracking system to collect data, but also collect data from, the sensor, snake kinematics. And at the end, he come up with a nice network that will predict the shape of the snake. Not only this, it's possible to predict when the snake will collide with an obstacle that could be hard or soft. And I didn't show in my presentation because this is not my work, it's Sharia's work, when he's even able to determine location a little bit where that contact is. So I see value in both, using a data-driven approach that will give us some good information, but also using the regular classical calibration process. I think it's also doable. It's a matter how much time you spend, before using the sensor, because data-driven requires a lot of work to collect and, come up with a model. And you have to be sure that your application will, whatever you are doing during data collection, it will happen in the real application.
Very true. Christos, go ahead, please.
What Julian is saying is very interesting. I think, that there are merits in both worlds. And I think what we need to always be mindful of the data-driven approaches is that they work for the system they have been developed for, because they can't generalize to another system, even though, the only thing you change the curvature, unless somehow you kind of train meta networks that could figure out, which subsequent path they should be taken. So the modeling gives you this flexibility. So maybe, in a setting where you have some fatigue, or whether where things might be changing, being able to update the models rather than the classical models, rather than the data-driven ones, could be beneficial. And the other thing that might be of importance is also how fast is your solvers, right? Because it could be that the system you have and maybe the motions you want to model is too complex for your classical models, whereas a data-driven model would be just, a lookup table essentially that would allow you to have very fast calculations. And perhaps even this is a starting point for then your classical model to go and solve. So I haven't seen combinations of the two worlds yet, and that might be something that's of interest.
A very interesting point of view. Yeah, you're right. So, the combination, I guess, to me also would be the solutions. We use the analytical approach and also data-driven approach, together, not just relying on each of those. Sam, what do you think? What's your opinion on the same question?
Yeah, thanks for asking me that good question. I think both are good. Pretty much, I guess, analytical approach is good, but as what Christos say, for some complex system, it's hard to model analytically. So we have to tackle the problem using data-driven approach. But based on my experience, I start working on I may be one of the first guy working on optical fiber intuitive surgical in 2008, because that was the start of iron system. I was the first one pretty much working on that. So at that time, I think, but one interesting thing is, because I was in the industry, I think what we found out most of the problem is not the modeling problem, is the attachment problem, is some sort of installation problem, reliability problem. A lot of time we make mistake in distinguishing the fundamental problem and kind of confuse ourselves. Sometimes it's just a mechanical defect. And then we try to model the mechanical defect. But after we build another new one, it disappears. So, and then when we improve the reliability process of building the sensor, attaching on the sensor, all these complex analytical model disappear, all the complex data-driven model disappear. And then we can always use very simple linear or nonlinear, one or two first order nonlinear model to solve the problem. So I guess is as what like Yulian say, is depending on your time. If you are rushing to present a paper in tomorrow or next week, then pretty much you will go for a low level approach. Because you don't have time to really build 100 instrument to figure out what's going on in the hardware. But if you have time, and then you really pay attention to all the details on attachment and all the sensor noise reliability, how to make sure every single fiber you get from the supplier is reliable and under really high quality control. If you go through all this process, you will be surprised. All the model we are using are very simple, very similar to the textbook model, without adding too much complex, crazy analytical solution. Of course, sometimes you still do use some sort of simple data-driven model to tackle the offset issue, but those offset issue is very easy to predict. A lot of time we say we need to have adaptive control to solve some problem, or some time-varying approach to solve some problem. At some point, most of the case, the manufacturing of the hardware is not reliable. That's why the property is changing. It's not the original property is supposed to change. It's just they didn't make it properly. So once you made the thing properly to be more reliable, all this time-varying property will be gone. And then you can always use a simple, very simple linear analytical model to solve the problem. So that's my personal experience, and that's why when I'm tackling those kind of hardware problems, I normally work with the student to pay attention to the installation detail, manufacturing details, and assembly details. And once all these things are well inspected, and we are very confident all the thing is well made and properly assigned, then we will tackle those problems using a very simple approach. And in general, it works, but maybe not good enough for publishing a good paper. But that's all I can say.
Thanks so much, for bringing up. Obviously, we need a reliable hardware before going to the sensing. If the hardware is not reliable, so we cannot blame control or like sensing. So we need to have that reliable thing. And I wanted to actually
is the confusion. It's not bringing them. Is sometimes when a student with only 1 or 2 years experience in the field, when they see some interesting behavior, dynamic behavior, they think they are discovering something new. Actually, I think this is normal. And then we found out there is a new type of friction property that is no one has seen before. But maybe they didn't. Maybe some part of mechanical system is half broken. That's why the friction is kind of halfway. And then, but after we change the hardware, everything become normal. And but we publish the paper already, and then say we discover a new friction property. And then try to model it with a highly nonlinear approach. I think those, sometimes I think if we have time, we have patience, then we may be able to solve a lot of fundamental problem using a simple solution and creating more reliable solution.
I wanted to actually ask you a follow-up questions regarding, you very intuitive, you said like for the ion system. My question is that how did they, I mean, they are using distributed, I guess, optical fibers, right? The one that Luna developed. So can you tell us a little bit regarding how you came up with that design? I mean, selection, let's say, so selection of those optical fibers, because as you said, those are very expensive for a medical device to use. So a little bit of background, I'm very curious to know. What was the, if it's possible to say, of course, it's not confidential.
We can say something general, I mean, but not really specific. But I think in general is I think you all know about ion system. That project started like 2008, more like from now is 13 years ago. So I was one of the first hire for that project, in particular working on control and the software and sensor. And I think pretty much as what I mentioned, like when you choose a sensor, the first idea is what's the requirement? Like we are targeting something on lung cancer. It's so small, the requirement is so small, the size is so small. And then you are looking for a couple millimeter, less than 5 millimeter diameter for the instrument. I think if you pay attention to the instrument on OS or like on ion is all less than 4 millimeter. So pretty much you cannot put any other sensor in that dimension. And also you are tackling some sort of sterilization issue. you may need to, in long term, you don't know if you want to do reposable instrument or disposable instrument. So, and also like interference, think about interference. If you are talking about EM sensor or other like electronic sensor, you may have interference. So there are not many options in the market that can allow you to solve that issue easily. I'm pretty sure people can seal off some other sensor properly, but within 4 millimeter diameter size, anything you add inside will occupy a lot of space. So try to make it clean, make it unique, and then flexible so that you can fit in other area. Then pretty much, I think you can easily find out maybe optical fiber is one of the good solution for that kind of application.
Great. So I had, if you don't have any other comments, the panelists on the previous questions, I wanted to ask another question. We just talked about like hardware aspects of the sensors. Then we talked about modeling data-driven things. How about fusion algorithms? Let's say we just say either like imaging modality or like embedded sensing. Do you think if we can like have fusing this data would help actually to have a better sensing? Any idea on that aspects? Christos, what do you think?
Yeah, totally. I think that would be the best way to go. Obviously, the fusion tends to give the best results. In our own experience, when we fused tracking information from fluoroscopy and even simple kinematic models, and then we were both able to make the tracking better and to do the 3D segmentations better as well, even if the kinematics were not correct, because you would, for example, be holding tissue and things like that. So even simple fusion of a couple of sensing elements, that can work very well. And so if you add to this, interoceptive sensing from perhaps the back end of the motors, or you have this sort of shape sensing together with the models, you can definitely get the best of all worlds. I have no doubt. So yeah, it's a matter of what can you really pack into your fusion setup in order to be able to combine. But definitely imaging and kinematics, I think this is a natural combination that can give you much better segmentations when you want them.
So for instance, for your robot, concentric tube robots that you use for the eye, so have you tried any of these type of like fusion algorithms, or it's just mainly teleoperation? Let's say you want to partially autonomously control your robots for your application, then sensing becomes very important, right? So in that case, what do you think would be the best option for your robot?
So we haven't tried that for the iRobot, but we did try it under a fluoroscopy system for a continuum robot that was more trying to investigate what sort of uses would have as a catheter, as a compliant catheter. And there we basically the tracking has image-based tracking has problems because you have a variety of bone structures and that do look like elongated bodies that the tracker would be confused with. So what we ended up doing was that the trackers would generate hypotheses, and then all these hypotheses will be coupled together with the kinematics, and then the kinematics would kind of weight these hypotheses and they would reinforce each other, and this ended up giving you from a single image a 3D structure as well, because you had the kinematics to bring the 3D information, and also kind of prune these hypotheses that really were not segmenting the robot. So in that context, yeah, it was definitely beneficial. And I can think also in the context of eye surgery or anything really. I mean, let's say you want to detect something, at minimum what you know is more or less how long it is. So perhaps what you should be detecting in the images. And ultrasound, definitely, I can see a very good combination there, especially all the robots, they have these reflective surfaces, they're pretty ugly. Coupling whatever you can do and segmenting images with your kinematic data, I think this can be the best. And I'm not very much aware of this literature, to be honest, but yeah, if nobody has done it, definitely it's worth exploring.
Julian, go ahead. You had some.
Yeah. Now it's a very good point from Christos. I guess we cannot say that whatever sensing technology you are using, that will work for everything. So we need maybe to try to have other type of sensing, or to do the fusion imaging, also kinematics. And so the continuum robot we are using for osteolytic application, that is a good example. Before we were talking about a model-based or a database. So in a model base, if you have a good model and you have a structure double the size, your model will work. But if you have data-driven, may not work. So you need to repeat, collecting data. Now, in our when we collected data for robot calibration, our discussion it was what kind of conditions should we set for our experimental experiments in order to collect realistic data. And of course, you cannot reproduce whatever will happen during the surgery. So in that case, our data is good and will give us good results for those specific conditions. And I mentioned when you collected data, it was also FBG data from manipulator, continuum robot kinematics, also tracking system for the grant. So we kind of put everything together. Even so, so the problem, we were able to control the snake in a planned motion. But once you go inside of the body, you have a more complex motion. Just to mention, our snake has inner lumen where we pass some tools that will cut and remove the tissue. And that means we have vibrations, we have maybe local deformation, so it's not enough. So in that case, at the end, what was implemented in the robot, because Sharia did some cadaver experiments, it was not only the feedback from the sensors, also feedback from CR, monitoring the kinematic parameters of the snake, implemented some virtual fixture to make sure. Again, we don't trust only the sensor, but we are able to capture the patient anatomy, and based on that, define a virtual fixture to control, to limit the snake motion. So the problem is a little bit more complex. Just sensor fusion, that will be still easy to be done. You come with sensing technology and you could fuse them, but the problem is a little bit more complex. It depends on what you like to provide. And it's not only to do the task, I think the more important is to be safe. So this is why we just put a lot of sensor in our robots.
Perfect. Sam and Emad, what do you think? Depending on your experience on the fusion of having multiple modalities.
Yeah, I mean, I totally agree with the point of view presented by Christos and Julian, but allow me just to mention the two different challenges here that we probably want to keep an eye on when we do data fusion. So why we do data fusion? Is it a clinical requirement? We really, for example, we need intraoperative data that's not sufficient, and we want to fuse it with a preoperative data that's coming in different time scale. And here we have a problem, two problems actually. One is quality control. To what degree we trust this 1 day old data or 1 hour old data that comes and play an action now. And the second, how we can visualize, how we can give this data and summarize it to the surgeon. So that's one flavor. The other flavor is, what if we don't have a problem with time? We have, for example, I do foot acoustics, so I can easily bombard the surgeon with 1 giga of data every second, because we have a foot acoustic at wavelengths that from 700 nanometer wavelengths with a step of 1 nanometer all the way to 900. So what he or she going to do with all these data? So it's important when we fuse these data to summarize it and give the right feedback to the surgeon during action. And as a matter of fact, we have this problem recently, and the doctor I'm working with, he told me, I don't need a oxygenation map or multi-wavelength imaging. All what I need is just 3 colors, red, orange, and green. Green means I'm safe, oxygenation is nice, and red means there is a hypoxia or a big problem happening here. So we started to take all this fused data from multiple wavelengths and just simply reduce it. So in short, I think there is quality control and visualization when it comes to the diffusion.
Amazing. Sam, what do you think?
I think all of them are speaking for the truth. I think they are all. I agree with all the idea. I don't. Depending on I think because sometimes if you have external imaging technology, because we have been talking about embedded sensing before. So embedded sensing can only tell you your own location. So you may not be able to tell you where you are at with respect to a global frame, or if you are targeting for some lesion, the lesion staying in the global frame, not staying in your local frame. So we still need some sort of external imaging sensing to help you to connect them together. So I think this is necessary. Unless you are purely talking about within the hardware, you want to put multiple instruments to enhance the quality of sensing, or some of the sensor you have for the hardware, which may not be sufficient to cover the entire configuration measurement for that particular hardware. But if you are talking about using different modality to cover the entire surgical scene, I think that's necessary. Because, for example, like optical fiber, they can only sense your own configuration. They don't know anything about the lesion you are trying to target at with respect to the global thing. You have to have some like X-ray or ultrasound or whatever thing to find out the correlation between you and other like a global frame.
Yeah, that's actually a good point. Maybe some algorithms, like if you have a pre-op data, if you use FPG, like a SLAM algorithm, I guess is something that we have borrowed from other communities and see where we are located, try to locate ourselves within the basically environment and then use it ideally in our case. So we are almost done. I had one more questions, like general questions. So if people want to work, like students are here, professors are here, do you think, what's the future direction for for sensing and sensing algorithms? If you want to suggest or work yourself on some directions, what do you suggest people, like in terms of worth basically trying that, like which is alive, a research that is alive for the next 4 or 5 years, not just for one paper, like ICRA paper or any other things? What do you suggest?
Well, I could start. Yes.
Yeah, definitely. I forgot to actually, we wanted to actually, Julian, if you can also connect it to OFDR and OCT, I wanted to ask, I forget, but go ahead. I mean, that's
right. So, well, first of all, if I will be a student and I would like to start now to do shape sensing, I will start with a review paper to see what is the state of art, and after that try to decide based on requirements as that I have to move forward. But shape sensing, it's a complex problem, because at the end, why do you need it? What is the reason? And actually, Matt made a good point. So we are able to detect something, but how we sense information to our users, the clinician, and what should be that information. And I will give you maybe one. Okay, about our snake robot. So at the end of the snake, we have some tools to remove the tissue, and this is a jelly-like tissue, and you like to remove until you reach the bone. So the problem is, are we able during cutting process to feel the force, make a difference between a jelly-like tissue and real bone? Because that will give me information until where I need to remove the tissue, and that is. So in that case, you are just cutting, you don't know what you are doing, you may take fluoroscopy image and say it's enough. But using this sensor, they could predict, if we train them correctly, they could predict until how much tissue I have to remove. So this is where, this is a direction that we haven't explored. We know that it's a good direction to follow. And this is how we will help the clinicians. So once you are cutting, we say it's enough, stop it. So we could reduce such a kind of margins. Now, in terms of evolution of the shape sensing, I will just mention definitely we are not able to catch the real shape of a regular needle. And, you know, there are a lot of PhD dissertation written on this with different, you know, approaches, different models. And we are still not able to put a needle into a tissue to say this is the shape of the needle. Okay, so in regular gel phantoms, yes, we are great, but not in real tissue. So we need definitely here to try to improve our, I would say, hardware, the fibers, distributed, you know, fibers that are able to capture also the torsion, and there are good work coming from Leuven, also from Canada, but on top of this is how you improve, you know, the accuracy, because sometimes if we like, I would like to go into the eye, my problem is 20, 30 microns, so I have to be very, very precise. Cut down the price, of course, and also to try to, you know, once you have a very complex system, it's a matter to try to put together different sensors. So that sensor fusion you mentioned, it's also a big issue that should be combined to work in real time and also to be safe. I'll stop here to let other people to give their opinion.
Perfect. Sam, do you want to go ahead?
I think at this moment in my mind, just two items. One is, can we have the shake, as what I mentioned, shake sensor is only for local sensing. So can we have any real-time imaging modality, really true real-time, not so-called like clinically real-time? Like when we take X-ray or intraoperative, like even the ultrasound is 20 Hertz. Can we do something like a kilohertz real-time sensing, or 100 Hertz or couple 100 Hertz real-time sensing from the external perspective? Because for us, we are robotic guy, we get used to 1,000 Hertz in encoder, which is so-called real-time sensing. But when we are talking about 10 Hertz or 2 Hertz, we don't think those are real-time, because when you do control, you cannot rely on those kind of, at least if you do good control, you need to have a sensor can provide you more than 200 Hertz or 300 Hertz closure bandwidth. So I think that's important. The second thing is similar to what Julian has said, is monitor the dissection process. Do we have any sensor? He was talking about mostly like a cutting. Do we have any sensor to monitor the burning? We all talk about the focal therapy right now, laser burning something. When we burn something, a lot of imaging are distorted. You cannot see something behind the image. So how much you have burned, which cannot be measured. So if we want to push the like a minimal invasive surgery to the next stage, that means we have to measure the margin before we cut it. So continuously in real time. So is there any other sensor, like a thermal sensor, or some people try to use MRI to measure the burning rate in real time? But if we don't use MRI, can we have other sensor to measure the burning rate in real time, so we know we have already complete cutting the exact number of lesion we want, instead of creating so much collateral damage? Right now, I think most of surgeons, what they do is create more than what we need. They cut more than what we need to guarantee they have removed all the lesion from the patient. But that may not be so-called a precise surgery. If we can cut exactly the same number of cancer we want without overkill something, that will be the ideal. I think at this moment, I haven't seen any good solution can help us to really fully utilize the power of focal therapy. Because when we burn something, we just based on gut feel and see like how much we burn, or we do dissection, or we do biopsy after that, which is kind of passive. Can we do a real-time sensing to learn how much we burn? Can we isolate the margin properly, precisely, without really doing those kind of biopsy tasks? That is the ideal case. Thank you.
Amazing, thanks. Emad, what do you think? I guess maybe photoacoustic or what you are doing answers like Sam's question. I guess, I don't know.
Yeah. I mean, in my talk, I try to answer some of your questions, and I'm not sure if I'm successful in getting all of these requirements, but definitely I can see it's reality that we can use photoacoustics to give you basically the cancer delineation in the margin. You can see it 4 centimeters before you get there. You can also see nerve and others. So, but back to your question, Farshid, you asked what is the exciting sensing algorithm problem for the coming 5 years, right? So I would say we probably one idea is how we can get volume imaging from single point. That's really, and if you think about it, we're simplifying the sensor, make it very simple to fabricate, very easy to integrate in any tiny tool, because now you only have a fiber 50 to 100 micron in diameter, and what it does is just send the light. And now the requirement, can we get from this, based on photoacoustic effect, a volume imaging for the anatomy, temperature mapping, cancer margin, nerve network. So this is quite challenged algorithmically. Not the device is very simple and trivial, but the part is how we can do that. And I may just mention one example, because I did not include it in my talk, is we did showcase that if we want to do, for example, thermal imaging, so back to Sam's, can we see the thermal damage without relying on MRI? Yeah, it is possible. Ultrasound provides this, but the idea here is we need to measure pretty much the time of flight and correlate that to the thermal dose. And we did show that we can, from a single point, single light source, generating photoacoustic wave propagating through the ablation zone, that this was sufficient to generate thermal map equivalent to MRI thermometry plus or minus 2 degrees Celsius. And that's for me, it's not a problem that can be solved in a year or two. This is really an outlook for 5 years.
Amazing. Thanks, Christos.
Yeah, I mean, I think, of course, it's work on whatever you feel is more exciting is the easy answer to give. But every one of these components that this workshop is touching on, the design, the sensing, and intelligence, they have open research problems that could feed 3, 4, 5 years of research. Like in the design, you have all these new systems, the growing robots, you have SMAs, you could have how do you make it so that it looks better in MRI, it looks better in ultrasound, or you lower the dose in fluoroscopy. So you start trying to look at this holistic approach as the workshop says, then I think new designs can be coming up in the terms of materials, in the terms of structures. Now on the sensing, sensing, I'm very interested in. I like it a lot. I hope we manage to have good shape sensing, good force sensing. But I think what I started saying, like, how do you sense what you're doing? And what you're doing is not only force. How much are you burning? Yes, you could maybe even there is this group at Imperial they do I think spectral analysis of whatever comes back by sucking the smoke, and they realize, is it tumor, is it not? So there are other groups that are looking at the sound, and depending on the sound, you realize it's different tissue. There are electrical impedance measurements. So what do you do? What can the tip of your robot do to understand how it affects the environment? And intelligence is also interesting. Now the caveat with intelligence is you have to be in a lab that has a working system, so you can add intelligence to it, because if you are building up capacity and building robots, you're not at a state where control is so good that suddenly you can add automation. But I mean, automation, collaborative robotics, can one robot hold something and the other pull it? This is also something of interest as well. So I think it's a very exciting topic. So hopefully, people will keep coming up with good ideas.
Awesome. Thanks so much. So we are almost at the end of the panel. I just wanted to ask audience, if you have questions, please go ahead. I see Mojtaba has question. Do you want to, Mojtaba, ask your question, or I can read that for Julian?
Well, I can see the question. Thank you very much, Mojtaba, for asking. So the question is, Okay, talk about electromagnetic tracking sensor for shape sensing registration and its advantages, disadvantages, especially for endoscopic brain surgery applications, and compare it with FDG or FDR sensor. I think here we have to consider two different aspects. The problem is what is our continuum manipulator? Is that it's very flexible or not very flexible? And you know, I don't know what you like to use in brain surgery application, but if you have something like a catheter, in that case, a distributed shape sensing, something that could be provided with continuum FBGs or FDR sensor, it's a better solution. If you have a kind of rigid structure like a snake, okay, or like a concentric tube, where you have some assumptions about rigidity of the system, and you will be able just to identify the strain and curvature and the shape in some specific points along the structure, you are still able to identify the shape sensing. Electromagnetic sensors, they are local sensors, so in that case they will work nicely for such a kind of let's say semi-rigid structure. But if you like to use that for catheters, that may not work properly. And by the way, Mojtaba, you should just double check. I think 2 days ago it was a paper coming from Emmanuel van der Porten from Leuven in collaboration with Ariana Menciasis about such a kind of combination. And they, it's a nice paper with sensor fusion. They show why only FBG is not working, why only electromagnetic tracking is not working, but putting together you could have good results. So that is a very nice paper. Now, OFDR sensor, they are also distributed, okay? So this is a good idea because you could lower the price of the FBG sensors. They are not cheap, of course, but keep in mind for OFDR sensor, you need a different FBG interrogators. The one coming from Luna, that is a cheap one, it's around 80K. So, you know, there are advantages, disadvantages. In terms of shape sensing reconstruction, again, is not, you cannot get the best answer only with one type of sensor. You need to do fusion. So I guess also for your application in brain surgery, you may decide to work to combine maybe two types of sensors. Again, your problem is to go, I don't know how close to the brain tissue, and it's a matter of safety and of course sensor accuracy. I hope I answered your question.
Perfect. Since you're advertising papers, Julian, you should have advertised a TRO paper as well on the sensor fusion. So we have a similar work actually fusing X-ray, intermittent X-ray data with FPG data, and then without knowing the model of the flexible robot. So I wanted to advertise our work as well. So any other questions from audience? Okay, perfect. So one last opinion from the panelists. I asked the same questions in the other panel. What do you think about this format for the workshop, right? This is obviously, we tried it. I mean, this is new, rather than I call it the passive, the traditional one that everyone just talks. And then everyone just listens and just one question. How do you think on this format? Because we hopefully are going to continue on the same topic, number 2, number 3, if we have time, obviously. So on the same time, what do you think? Any feedback, any comments regarding this? Sam, go ahead. Your mic is open.
No, I just smile. I still prefer the traditional one. I mean,
okay.
Because after people give their talk, people can have follow-up question right after, which may be good. Because sometimes when we have a panel discussion, we touch on so many topics at the same time, we don't have focus. But and we can try something new every time, but I prefer the traditional one. Yeah.
Okay, good to know. Julian, what do you think?
Well, if we are talking about this virtual versus in person, that is traditional, definitely traditional. Now I will just log out and go to my next meeting. I'll forget about all the questions. So, but if I will be, in person, I could talk more with Mojtaba to explain, because the story is much longer. But yeah, I think virtual is good if the audience is happy with the feedback. But I don't think it's enough.
Mm-hmm. So mainly my question was on the format of the panels, not just recorded talks and then just panel discussions. Yeah, that was actually the critics of Sam. He wanted to just after the talk, just talk about that topic. What do you think on this?
Well, I will say this is a kind of classic when we go to a workshop, or we are doing our talk, and at the end we'll say, okay, all the speakers come here on the stage and let's have such a kind of discussion. But I think it's definitely a good model.
Okay, cool. Emad and Christos, what do you think?
Yeah, I really like it. It's a really good change, but maybe if there is a way to have the discussion more involving the audience, not just the 3 or 4 panels, that would be really nice, because it's an opportunity for people behind screen to ask questions, to have active discussion. So
cool. All right. Next workshop, if they accept it. Christos, what do you think?
I mean, in the context of virtual workshops, I mean, I've been in the audience of panel discussions, and I have to say I enjoy them more than listening to talks. I mean, this depends. So I tend to like panel discussions more, especially if the questions come from the audience. They can trigger debates and things like that. And I think a combination where there could be some introductions of the speakers before, which is what you did, but in the context of the recorded presentations. So I think such a format would transfer well. It doesn't deviate too much from what we have been used to. And I have to say, I enjoyed it. I enjoyed the conversations. And I do feel if it was a physical one, the audience would participate more, because it just, you have the more intimate interaction and approach. Yeah, perfect. I think it's, I enjoyed it a lot. It was very, very nice to hear everybody's viewpoints. It was great.
I appreciate that. Yeah, thanks again. Thanks so much. Specifically, Christos, you and Sam, because of the time. Sam is almost, I guess, I don't know, is it like 1 a.m. or something? Thanks again for, putting the time. Thank you. Appreciate that, of course, Emad and Julian for joining us. So one thing, I guess I mentioned to panelists, to audience again, we have a bunch of questions as a poll. There is a link in the workshop website that we are asking you a couple of questions regarding the topic of the workshop. We are going to collect this statistical data and hopefully write a review paper regarding these ideas, regarding the perspectives of the panel. And we would like to actually get your feedback. We would appreciate actually if you can answer those questions. With that, I'm going to end this panel. So we are about 10 minutes ahead, I guess, of the basically workshop schedule. So let's have a 10 minutes break, and then we will have the next videos, recorded videos of the third panel. And thanks so much again.